I am Neeraj Gartia, and I'll be presenting today about how can we monitor an Ubuntu server with Prometheus and eBPF. Yeah. So by the end of this session, you guys will know how we can connect two powerful tools eBPF and Prometheus to monitor an Ubuntu server. So here are some metrics about me. I am Neeraj Gartia, and I work as a software engineer at Microsoft, and I am also a Prometheus contributor. I have been contributing to Prometheus for the last 1.5 years, mainly contributing to ROMQL, and also I was recognized as a Grafana champion for my contribution to Prometheus. So yeah, let's deep dive. So here is a quick question. How many of you are familiar with Prometheus or Grafana? Please raise your hands. Yeah, that's a good number. So for the ones who don't know, I'll be covering about that as well, so that we all are in the same page. So here is the today's agenda. First, I'll introduce all about Prometheus and Grafana, and then we'll see why system level monitoring is important, and then we'll see node explorer, then eBPF, and then what eBPF adds to the traditional metric exporters, and then I'll talk about some best practices as well, and there will be question and answers. So now let's talk why monitoring matters. So mainly there are three reasons. First one is system health. So we want to know how our system is performing. How is the CPU health? How is the memory? How is the disk? How is the network? And how other resources are currently performing? Are they healthy or not? And also small anomalies in these resources can lead to a large outages as well. So we need monitoring the system, and not only for system health, we can use monitoring for debugging purpose as well, so that if let's suppose a outage happens, then we can it's like a flashback type of kind of thing. We can go back to that time, we can see the logs, we can see the metrics, and you can correlate that these things happened and that's why the outage was there. Also, we can use monitoring to tune performance as well. So we can see whether we met the SLO or not for a product. So there are mainly two types of monitoring layers. First one is application level monitoring, another one is system level monitoring. Application level monitoring means what happens in the application, such that the request rates, the error counts, the response latency, these comes under application monitoring. But for system monitoring, we generally talk about the CPU health, memory usage, and then disk IO latency, network calls. All these things comes under system monitoring. So in this talk today, we'll mostly talk about system monitoring. Yeah. So yeah, as I told you all about that, I discussed about Prometheus and Grafana. So let's talk about them. What is Prometheus? Prometheus is an open source monitoring system. It is basically a time series database which stores matrices in the form of labels. Labels means key value pairs. So different matrices have different key value pairs. And also it is a pull based model, and it has a very strong and powerful query language called PromeQL. And what is Grafana? Grafana is a visualization tool. So you can customize your dashboards for different matrices, you can have alerts for them, and also it integrates seamlessly with Prometheus as well as other data sources as well. Maybe something like Excel sheet as well will work with Grafana as well. Yeah, so let's quickly go through about the Prometheus architecture, how it works and what it is. So in the center there is Prometheus server, and it has mainly three main purposes. It retrieves the data or the matrices, it stores inside a TSDB, that's a time series database, and also it exposes the metrics using a HTTP server. And what are other things? There is push gateway, that is for short-lived jobs, There is exporters which exports the metrics to Prometheus. There is alert manager which helps in alerting if something like there is a outage kind of thing, then it can alert to different channels like email, PaperDuty, or even Slack as well. And also you have PromeQL, which is a query language to query the matrices that are stored in Prometheus, and which can be used by different visualization tools such that Prometheus Web UI, Grafana as well, and other API clients as well. So yeah. So now let's talk about what are the different metric types in Prometheus. Mainly, so there are only 4 types of matrices: counter, gauge, histogram, and summary. Counters are only provides a single value at a single timestamp, and they are monotonically increasing, such that total number of requests served by this server, total number of errors, like that, which should increase monotonically, should be used as a counter. But on the other hand, gauge is like a value that goes up and down, like CPU temperature or memory usage, number of concurrent requests, like that. But here things come like gets more interesting. Here we have histogram. So the previous two data types have only a single value at a single timestamp, but histogram supports multiple value. Histogram has multiple values at a single timestamp for a single metric, and the observations are broken into different buckets according to the, let's suppose the we want to export the request latency as histogram, then we will categorize them into different buckets. Let's suppose from 0 to 1 ms and 1 ms to 2 ms, like that, and we will store these data into a histogram. And summary is similar to histogram, but instead of buckets we have quantiles. And one major factor that differentiates between histogram and summary is that we cannot aggregate summary, but we can aggregate histogram. So histogram is more handy and more useful than summary, but that depends on your use case. So here is an example of a histogram that Prometheus provides. Here, so you can see different buckets, less than 0.25, 0.25 to 0.5, like that. There are different buckets, and corresponding to that there are different values. And the histogram in Prometheus are cumulative. So here you can see HTTP request duration seconds less than 0.25, it is 3, less than 0.5, it is 9. That means everything less than 0.5 will be considered. So these buckets are cumulative in Prometheus. So now let's talk about what is node exporter. Previously during the Prometheus architecture I talked about the exporters. Here is an example of an exporter. So Prometheus is a node exporter is a go-to exporter for Prometheus. It exports different system level matrices to Prometheus, such as CPU usage, memory usage, the like number of TCP transmission happened, like that. And it is very lightweight, and it exposes metric via HTTP endpoint. And why it matters? Because it provides a system level visibility. Also, it covers CPU, memory, disk, network, and processor, and it is a baseline of system monitoring for Prometheus. But it has some limitations as well. Not all matrices are exported by node exporter. It only exports the stats that are in /proc or /sys. So yeah, let's see what are matrices that exports node exporter. So here is CPU. It exports the CPU utilization, load average, context switches. For memory, it exports memory usage, free versus cached memory usage activity. For disk, it exports IO rates, space usage, and all these things. But one thing that needs to be remembered is that all these metrics are only counter or gauge. Node exporter does not export histograms. So they only export only a single value at a single timestamp for a single metric. So now let's talk about a scenario. You have an application running, and in the application monitoring layer, you saw a sudden spike, and that is in the DB query latency. Now, the node exporter metrics looks all normal, everything is fine, the CPU usage, the memory usage, network, everything looks good. But something is wrong, and we don't know where is the issue. Another thing I forgot to mention is that we don't have a monitoring layer for database in this scenario. So what are the possible reasons for this spike? There might be disk IO latency spike, there might be network latency as well, or there might be system call delays or kernel scheduling, or database logs could have been the reason. But we don't know. Node exporter didn't provide any such information to us. So we need a deeper visibility. What we lack is a granular latency distribution or histogram-like metric. We only have averages in this scenario. Node exporter only provides us averages, not actual distribution. And we need visibility into the system calls, what is happening to the system calls, how the IO latency is there for the disk, and what is the network retransmission, and how much the network drops is, and what about the kernel events, what are the events and how they are performing in this scenario. So here comes eBPF. And what is eBPF? eBPF makes Linux kernel programmable without harming, and it is very safe. So eBPF is eBPF helps us running a source code in Linux kernel, and it is very safe, and so it is very safe, efficient, and flexible way to extend our observability and security as well. So here is a diagram about how eBPF works. So on the top there is user space. So in user space, all the apps that are running, and between user space and kernel space there is system call interface, which acts as a bridge, and from the user space we inject the eBPF code. eBPF code runs inside the kernel space, and it exports data to the user space. This is basically what happens with eBPF. So how eBPF works? It has mainly four different components. The small piece of code, obviously, the program that will run, and also it has a map that is a key value pair, which is virtually shared between the user space and kernel space. Also, eBPF programs are attached to events, and also it is very safe because it is verified before execution, so that there should not be any crashes, any infinite loops, or memory safety is guaranteed. So let's see a deeper insight. So let's suppose there is a process which injects the eBPF program using system call, and then there is eBPF verifier which verifies that this program is safe, and then this program goes to the JIT compiler, which compiles the eBPF code into machine codes so that it can be run inside the kernel. And this eBPF code acts like hooks itself to different system calls, such as network sockets, DiskPIV, different kernel events, and user space proofs as well. So what are different eBPF attachment points which we can hook the eBPF program? Let's talk about that. So we have the kernel probes or kernel return probes. That means whenever any kernel function runs, we can attach or hook that eBPF program at the starting of the kernel function and at the end of the kernel function. Also, same goes with the user U probes and UVet probes. That means user functions and user function returns. Also, we can attach it to the hook it to the trace points so that we can have the tracing data as well. Also, we have perf events, USDT, and networking hooks as well. So here are the instrumented process loads the eBPF program. It then listens or hooks itself to kernel probes, perf events, etc. And then it stores the data inside this eBPF map, which can be read or written by this instrumented process, and it gets the data from this map. And also there is uprobes as well, that is linked to another process, and this eBPF program can hook itself to this uprobe as well. So what are the use cases of eBPF? So for monitoring, we can use eBPF, we can hook itself to networking stacks, and we can trace the packets, we can measure the latencies, we can detect the bottlenecks from there. Also, we can attach to the disk as well, and we can see the disk IO latency, you can get the disk IO delays, and we can pinpoint the slow devices, like what things are slow. Also, we can like attach or hook them into system calls as well, and we can monitor the system calls, we can measure the latency, and we can see what happening inside these system calls. And this is a very famous diagram in eBPF world, and BCC is BPF compiler collection, which provides different library kind of thing that is Python based, so that we can use eBPF efficiently. And so these are different tools that BCC provides. So in the application layer, we have MySQL slower, which tracks the MySQL query latencies. And here we have Ilsno in the system call interface, which tracks how many how many processes are killed, how many processes are executed here. And here in the network stack we have TCP top, TCP live, TCP connect, TCP asset early. So these are a very high level diagram of the tools that are provided by Linux BCC. Yeah. So we talked about that how we can use eBPF for monitoring. So we don't have to write that big line of code for exporting the metrics using BPF. That is already done by Cloudflare. So Cloudflare build an open source eBPF exporter, which exports these metrics that are from eBPF to Prometheus, and it supports Prometheus and it integrates with it seamlessly. So it goes beyond the node exporter. How? It provides different latencies as well. For example, disk IO latency, accept calls latency, etc. And also it is customizable. You can write your own C code to run the BPF program for monitoring as well. So how eBPF exporter fits in? So eBPF exporter injects the eBPF program inside the kernel. eBPF verifies the program, and if it is approved, then JIT compiler compiles it, attached to the trace point, and if there is an event, then sends the data to the map, and then eBPF exporter reads and writes the data from this map and export them as a metric, and the Prometheus instance will scrape these metrics and we can visualize them in Grafana. So here is a sample C code for eBPF exporter. So here is a trace point. So here it is block request complete. That means whenever a block request is completed, this function will be run. And what it does is it first gets us at the delta between the start timestamp and the end timestamp, which gives us the time taken by this block request to complete, and then it stores this data into a histogram, which can later be exported to Prometheus. And here is a small YAML code as well, which we can use for the eBPF exporter. Here it tells about the name of the metric, bucket type, then bucket multiplier, and also it provides different labels as well. So here are some graphs from eBPF exporter that it provides. Here you can see there is a heat map, but these type of heat maps are not present in node exporter. It only provides these kind of graphs. Only these types of counters are exported by node exporter, not these type of heat maps. So that is an additional thing that eBPF exporter adds. And for the disk as well, there are different heat maps for disk I/O latency, file system I/O latency, and their P95 percentile as well. And here are some for system calls as well. System call totals and system call error totals. So now let's go back into the spike that happened and why it happened. So what node exporter missed? No system call latency was there, no disk I/O latency was there, no per process scheduling delays was there. It only gave us average values. So at that time, at the spike, the average value would have risen. But we don't know, there might be the number of requests would have risen, so that average value was higher. We don't know actual distribution. Was there any outliers in the latency? We don't know anything about it with node exporter. But what eBPF exporter adds is kernel level histograms. It gives us histograms so that we can check what are the outliers, and if there is any outlier, what is the reason. That these things you can check with eBPF exporter. And we have per disk, per network, per system call insights as well, and you can see the real cause. So since these deeper visibility into the root cause was there, so we identified the main issue. And so let's talk about the best practices for eBPF in monitoring. First, not every kernel is compatible with eBPF. Some are compatible, some are not. And also we should always write safe programs. Although the eBPF verifier verifies the program, but still it is a good practice to write safe programs. And also without any alert, a metric is of no use. If we only see the metric there, if there is only a metric and no alert, then you cannot know that if something wrong happened with the system. So we should always integrate alerts as well, and also we should not overkill. So we should not overkill things. So the least things we should only monitor that are required. And also there should be security consideration as well. While running the programs, we should give least privileges, and don't download or run any random code from GitHub, because it runs in kernel and it might cause security issues. And so last thing is when to use node exporter and when to use eBPF exporter. So node exporter gives us a good insight, average values of the system. But if there are something that are inaccessible through normal direct instrumentation or node exporter, then we should use eBPF, because with eBPF we don't need to change the actual code of the application or the server. It only runs in the kernel. So if there is something that is inaccessible from using the direct instrumentation, then we should only use this eBPF exporter. And since it runs in the kernel, there might be some performance issues as well, so we need to consider that as well. Yeah, so these are some key takeaways. And so system monitoring is essential to monitor the system's health. And also node exporter is a lightweight exporter which provides us a broad level system health, but eBPF gives us a deep system health matrices, and it gives us granular kernel level observability, and both are complementary tools. Node exporter is very lightweight, and also it gives us averages, but eBPF gives us latencies, histogram distribution. So according to our requirement, we should choose between these two exporter, and then we should use. Yeah, so if you guys want to learn about these, you can see the Prometheus docs, and also if you have any doubts, you can ask in Prometheus Slack channel as well. They are always active and they reply very fast. And also here are some eBPF resources, and you can visit these GitHub repositories as well. According to some benchmarking, eBPF exporter is slightly around 2% more overhead than node exporter. So it comes with a cost. If you want to get kernel level insights, then you have to pay some cost. There is a cost associated with it. I said about there is a verifier that runs before executing the eBPF code. It checks whether there is no infinite loop, no memory leaks. That these things are already checked. After that, it runs in the kernel, so it is safe. Yeah, so the exporter that is built by Cloudflare already has some examples of the C code for the eBPF exporter. Also, they have written YAML code as well, so you can check that. And I think all these examples are sufficient for the use cases. But if you have anything, then you can write yourself as well. No. You need to change only the eBPF code. The C code that you write, that only needs to be changed. Flame graph, I mainly contribute to Prometheus, so I don't have much idea about Grafana dashboard. I don't know much about that. I mostly contribute to Prometheus.